Rob Gorney here. Welcome to the June installment of the Forge Modeling Simulation Community Meeting. Have exciting presentations for everyone today. Just go to my next one. Sorry. So two primary people presenting today. John McClellan is able to join us to give us an overview of the 16A stimulation activities. I know I gave a very brief highlight last meeting, but that was very brief and essentially nowhere near the thoroughness and the full detail that John will be able to give us today. And then following John, Peng Xing and Branko Demjanic, we'll just give a very brief, very quick overview of some initial comparisons between the pre-stimulation modeling that we did as part of the Forge team with the field observations. And following that, I think we'll be able to talk about some path forward as we're going to move on. But before I turn it over to John, I just want to say one thing, because I know that everyone is thinking of this. It's going to tie into our future plans. It is some of the data availability from the recent stimulation. So, John, correct me if I'm wrong here, but for the pressure and flow rates from the field experiments, those are on GDR now, correct?
As are the tracer data.
Oh, okay. That was new to me. I didn't learn that yet. So, essentially what we're trying to do is get a complete data set for everyone in the modeling community to be able to do your own simulations or work with us on simulations. Some of the data aren't in yet. So, the pressure and flow rates, as I said, are there. Microseismic, we hope to have by the end of June. For all these are being post-processed now. Some of the water samples and tracers, I lumped those together. As John just said, the tracer data are available now. I wasn't aware of that. But the water samples, I believe, Stewart is on. But we're hoping that maybe by the end of June, we'll have some water sample data. Water was collected pre and post injection. It's being analyzed right now. As soon as we get all this together, we'll make sure we make a note out to everyone. And the last piece I have on here is strain data. We did have several surface locations that were monitored near surface locations. Some of the telemetry with those instruments had some issues. We talked to the researchers. They're working that, but it's going to require someone to go to the site and actually collect the data. I'm not sure where that's at, but I'm hoping we'll have that here very, very soon as well. So that's all I really wanted to say. We could save questions and discussions until after all the presentations. But I do want to say, once we get all these data together, we will actually put a little, we'll email out the group with GDR links to all the data sets. So it'll be easy for you to find them and make sure you find the right ones. We realize there are, if you go to GDR to try to find some of the data, you can get lost and go down pretty deep in the rabbit hole and not necessarily find exactly what you want. So we'll put a summary of the links to these and send them out to everyone that's on the mailing list. With that, I'll stop sharing and I'll turn it over to John.
Thank you, Rob. We'll just give a brief introduction to the stimulation activities to provide context for the discussion, the presentation by Peng Zhu. And just to put this into perspective and I know many people are familiar with this, but let's just indicate where we are here at the Forge site. We have drilled the injection well, that's 16A 7832. And what we'll talk about today are 3 hydraulic fracturing stages at the toe of that well. And those facilitated collection and location of microseismic events that will guide the drilling of subsequent well 16B, sometimes towards the end of this year, first of next year. And then the rest follows subsequently. So to put this into perspective and to remind people, especially for those who aren't particularly familiar, 6 wells have been drilled at this site. 5 of those wells were drilled for reservoir characterization, for in situ stress measurement, for coring, for logging, and to be used as monitoring wells when stimulations are ongoing. The injection well 16A, shown here in white, had a trajectory drilled at 105 degrees south of north And that was in the inferred direction of the minimum regional principal stress, so that multiple transverse fractures could be potentially created across the length of this particular fracture. And one of the points that I want to emphasize here is that what had to be dealt with in this particular fracturing campaign were the temperatures. And you can see the temperatures towards the toe of the 16B well were about 220 degrees centigrade, static reservoir temperature. And so in terms of that, temperature is what was one of the challenging factors, finding isolation devices that would work under those temperatures. And secondly, comprehending whether there are treating fluids that can be viscosified and tolerate those temperatures. The second thing that is on the books as a scientific objective for the stimulation treatment was to try and understand the role of the natural fractures. So at the left is an outcrop of the actual Forge reservoir, a few kilometers away. And despite exaggerations because of de-stressing and erosion, one can still infer that there are, say, 4 dominant fracture systems that will exist in the reservoir. And those have been extensively mapped and used for DFNs, as you will hear. The question arises that how significant those natural fractures, what role those natural fractures are going to play. And you'll hear more of that from Pongju and Bronco. The second issue, from an operational perspective, or the third issue, we're talking about temperature, we're talking about natural fractures, and we're talking about the ultimate success of EGS type operations is the ability to connect between 2 wells. And the basis here is drilling the injection well first, and then doing a trial fracturing campaign, which we'll talk about. And this is based on learnings from the Fenton Hill work, where an injection well and a production well were drilled, and they were sited, but much of the activity occurred away from the corridor between those 2 wells, and there was not a substantial injection interaction between the 2 wells. And so those were the goals: overcome the temperature issues that are manifested here in this particular picture of degraded packers that we've commonly experienced, and successfully monitor the fractures so that we can determine how to drill into those fractures. And I've shown this slide many times before to people, but the issue here is that the fracturing strategy is not substantially different than what was done at Fenton Hill. Pumping slick water at Fenton Hill in December 1983 for a large frac that was done there. About 6 million gallons of fluid, just under 6 million gallons of fluid were pumped at 50 barrels a minute and carried, and it was slick water. And that slick water did carry actually some fine calcium carbonate that was selected as a fluid loss or diversion agent. What was done in the particular well here at Forge, shown in cross section and plan view here, was to pump 3 stages that were not substantially different to the Fenton Hill stage, other than in terms of their volumes, that they were less. The first stage was pumped in a 200-foot long open hole section, and this was slick water. And as you gathered from the previous discussion with Rob, there were tracers pumped. There was a unique organic tracer pumped in each stage of the treatment. So the first treatment was slick water at rates up to 50 barrels a minute. The second stage moved up into the casing, and the first stage was isolated with a bridge plug. And this was one of the successes of this treatment, the effectiveness of interwells bridge plugs. It was a bridge plug was set, it was perforated, and slick water was pumped at rates up to 35 barrels a minute. The third stage moved uphole a little farther, Both of these stages were sited in areas where the geoscientists had felt that there were enough natural fractures that would facilitate breakdown and fracture growth. The difference with the third stage was that it was a cross-linked CMHPG. As I mentioned, one of the issues, the important issues, we had a lot of experience in previous wells with failure of either bridge plugs or packers, and so we sought out bridge plugs from Interwell. These were able to tolerate temperatures, the bridge plugs themselves. However, the setting tool, a wireline setting tool, could not tolerate the temperatures, and so this required bringing in a rig. Nevertheless, the plugs worked effectively. So once again, we'll go back to this picture that we're treating down 16A, a 65-degree inclined well, drilled to the east-southeast in the direction of the minimum principal stress. 3 stages done at the toe of the well, and 3 wells had geophones and in them for detecting and locating microseismicity that was associated with these treatments. There was also a DAS cable down to about 3,000 feet in well 7832, and a DAS cable down to about 3,000 feet in 5632. So the first stage, in advance of the first stage, we did a small low rate injection test just to see if there was any indication that shear stimulation would occur. In this particular test, pumping at rates less than half a barrel a minute in general. Pressure built relatively quickly and leveled off, and just indicating some sort of fracture opening had likely occurred. As I understand it, there was limited seismicity that was associated with this injection. Now, that may not be too surprising because after the well had been drilled a year or so earlier, immediately after the well had been drilled, we ran a defit in this open hole section, and we did a low rate injection and a conventional defit. So if one is presuming the viability of the Kaiser effect, you may not see substantial additional seismicity. Nevertheless, immediately after this, we pumped the first stage, and that first stage was all the frac work was done by Liberty, and we pumped down casing into the open hole section, about 200 feet of open hole. And as you can see from the plot here, we have surface pressure marked in red, and we have rate marked in green. Rate has the scale on the right, and pressure has the scale on the left. And we walked it up in 5 barrel a minute increments because we were kind of uncertain what was going to happen. And we took it up in those increments to 50 barrels a minute, held it at 50 barrels a minute, and then shut down. And you can see from the surface pressure that after about 50 or 60 minutes, the surface treating pressure was relatively agnostic to the rate. This well was shut in for a brief period of time. Our goal here was not to do defit type measurements, but to carry out these treatments. It was shut in for about 4 hours, and then it was flowed back. It was flowed back so that we could recover as much of the tracer from this stage as possible that was going to flow back to minimize cross-contamination between stages, and also to eliminate any potential for stress shadowing. That we've seen some indications in previous smaller volume treatments that there could be some interactions. After flowing back this particular stage, and that was a slick water stage without proppant, we set the interwell bridge plug above that zone. You can see the element itself at the left, the bridge plug being run in the middle. Then extreme wire line went in with a 20-foot long gun, single cluster we just wanted to simplify the fracture geometry that was created, and we ran a relatively long gun so that we could maximize our opportunity for finding initiation points associated with natural fractures. So isolated, perforated, treated. And the second treatment, as you can see, we pumped a little bit less fluid. As you might recall from the previous slide, we pumped about 4,500 barrels in the previous stage. This one was 2,700 barrels, pumped at a slightly lower rate, recognizing the potential for perforation loss and near wellbore loss. And I think you'll hear more about that in the following talk. Now, and you can see, recalling once again that red is pressure axis on the left and green is rate axis on the right, that there were two intentional shut-ins. In the 5 barrel a minute stage, immediately at the start, there was a shut-in so that we could look for any sort of water hammer effects. And the reason that we were doing that is that Momentum AI was monitoring surface pressure, and that surface pressure was being monitored, and we wanted to compare the initial shut-in at 5 barrels a minute to an end of job shut-in at 5 barrels a minute, and see if there was any difference in the water hammer and other effects that were recorded. You can also see that during the middle of the job, there was a shut-in in the middle of the job. And the intent of this was to evaluate whether there was any seismicity that was preferentially associated with a rapid change in rate, either going down or coming back immediately, or coming back rapidly to 35 barrels a minute. The jury's still out on that. We have not specifically seen the details of the microseismicity. So this treatment was pumped, it was shut in, slowed back for 12 hours. And we moved on to running a bridge plug and perforating for the third stage. The third stage was similar to the second stage at about 35 barrels a minute. I don't see the exact volume of fluid pumped here, but it was about 2,500 barrels that were pumped at rates up to 35 barrels a minute. We pumped low concentrations of micropropant, as much as anything, just to see whether or not there was any sort of difference in the fracture morphology from the seismicity or whatever. And once again, I think it's premature to make those evaluations. Oh, I'm sorry, we did pump 3,000 barrels, slightly more because of some issues in actually running the micropropant. Once again, this well was shut in for a brief period of time and then flowed back with flowback rates and temperatures being and tracer concentrations being monitored at the surface. So this is one of the stages that we do have some preliminary seismic work. You can see from the pressure indicated in red. This was an unintentional shut-in, equipment related, quickly resolved. That it is a decaying pressure, somewhat indicative of what one would take to be pseudo-radial fracture growth, and that morphology is supported, I think, by the preliminary picture of seismicity that we see on the right. The seismic data was acquired and under the supervision of geoenergy sweeps, and it was a fantastic success here in acquiring these data. So the well was flowed back, surface temperatures in excess of 200 degrees Fahrenheit, and subsequently the 2 bridge plugs were successfully removed without issues, and preliminary tracer data shown here, showing, I think, that there was little interaction with the tracer from stage to stage. You know, the jury's still out on that, but the only time we really started to see tracer 2 and tracer 1 during flowback after the end of the job was after the bridge plugs were removed, and that's consistent with that happening. So the next stage will be drilling the 16B well to try and intersect those fractures. And we'll look to do that in December, January coming up. And once again, it's a 50-year march from Fenton Hill, and we're very much appreciative of the DOE funding. Rob, that's it for me.
Thank you, John. And I think everyone, let's hold questions. John, can you stay on to the top of the hour?
Sure.
Okay, so we'll hold questions then. Pengju, Branko, do you want to take over the screen and show your presentation, please?
Okay, let me share my screen.
And I want to tell everyone, congratulations to Pengju. He's a proud father of a new baby girl as of like, what, 2 weeks ago now? He seems like he's getting some sleep, so his eyes aren't bloodshot anyway. So congratulations again.
Thank you. So so here we just want to open discuss about this stimulation data, especially the pressure data. So here I will partly repeat what John showed and refresh your memory. So so here we have 3 stages. Here's stage 1 with lake water and open hole completion. And the pressure profile looks like more flatter than the other 2 stages. So the second stage is case and perforation, and with also slick water. And so we see just from the surface pressure, it's kind of decreasing after like 17 minutes. And again, we have a stage 3. It's also case and perforation, but here we use cross-link gel, so surface pressure also decrease. So this is the pressure data we get from the stimulation, and then I will do some calculation based on that. First, is calculate the bottom hole pressure and net pressure. But this is not easy job because so first so we know the surface pressure, so we add the hydrostatic, we get the bottom hole pressure, and we so the bottom hole pressure subtract SH mean, we get net pressure. So SH mean here I use a 0.78 psi per foot. So this basically like about in the range of the defeat test we have done as a total of this well. So here we get net pressure, but that's not correct because we need some this friction, right? This pipe friction for stage 1, and for stage 2 and stage 3 you have perforation. You have perforation friction. So we need to consider the friction. Then we get the net pressure. So stage 3. Okay, here. So if you look at this upright figure, here's how I calculate friction. So because we have the step down, so after this peak pumping rate, we have rate step down. So each rate step down, the difference between the different rate is a friction. So, and you add them together, so you cannot get the friction at different pumping rate. And then you apply this regression formula to this injection part, the increasing rate part. So you subtract this friction, then you get the net pressure. So, so this orange line here is the net pressure. So after the friction correction, so it's basically the surface pressure plus the hydrostatic minus SH mean, then minus the friction. So here is the net pressure. and this lower figure is simulation. A simulation we did before, so we haven't done any new simulation. This is simulation we did before the stimulation. So we did a lot of simulation following this planned injection rate and consider different kind of DFN. So here's one case, and this blue figure, the blue line show here is the pressure of the simulation, and in this case we have permeable and frictional difference. So the friction angle is like 37 degree, and is initial permeable. So see the comparison between the stimulation data and simulation data, and so yeah, as I said, we have different cases, and then we compare to another case. In this case, so it's a extreme case. Let's say so like the natural fractures are either very, very strong, or they are not like give any influence of this hydraulic fracture propagation. So you generally get a pan-shaped crack. So here we compare the net pressure of the stimulation with simulation. So again, like we compare these two cases, and this you kind of explained by both models, and looks like this second one is closer, has a closer trend. But so what we can do is so the fracture geometry. So we have like 3 monitoring wells. So we have microseismic data. So we will know, like we get more like confidence on the fracture geometry after we get the microseismic data. But here I just want to show you like how different models like compared to the stimulation data. And here's the stage 2. Again, so I did the friction correction by this step down data. And so here, the orange one is the net pressure of stimulation, and the blue one is our simulation. This is pan-shaped crack. So this, so the pressure cannot match after like 60 minutes, but like of 40 minutes. But at the beginning, we have a really high net pressure, like according to my calculation. But we all believe that's not true, right? You just cannot have like 3,500 psi net pressure. So we believe there's some something related to the completion, because we didn't. So as in the open hole, if we go back in the open hole section, at the beginning we don't have that such high net pressure. Imagine that. Think about that. So we have at the beginning from stage 1, stage 2, they have same pumping rate, 5 barrel per minute, and same fluid, silica water. The only difference is the completion. Then in stage 1, we are in open hole, and in stage 2, we are in the perforation zone, case section. So the completion must contribute to something to this high net pressure. So one reason that's because you correct the net pressure based on the step down data, but these things maybe not apply to the beginning, because at the beginning you may have fewer perforation holes taking fluid, and at at later time, you have more provision holes taking fluid. So this is one possible reason that contributes this high net pressure. And we also compared to, again, the like friction on the weak DFN case, but this case, the pressure profile is quite different from stimulation. So this in stage 3, similar thing. Do the friction correction based on the step down data. Again, we see this high net pressure is like it's about 4,100 psi. Again, there's could be related to the completion, the perforation, so in this. And again, we compare to another weak and the friction case, and in our simulation, it has increasing pressure. So it's quite different from stimulation. So generally, in this 3 stage, so I put these 3 stages together. So stage 1, so this are all stimulation data, decreasing the trend of the net pressure, so they all can kind of match to a penny-shaped crack. But for the for stage 1, it is also possible that you match to the case with the friction and weak DFN. So yeah, as I mentioned, the high net pressure, like net pressure, I calculated 3,500 to 4,100 psi at the beginning of stage 2 and stage 3. It could be like you have a small number of provision holes at the beginning. I gave you a large provision friction, and these these things cannot be maybe not reflected in the step down data. So that's you don't have a correct provision correction at the beginning. So another reason could be the red wall heterogeneity. So the reason I say that because we have a core from this this well. So in some regions, like it's granite. Like if you look at the core, all the like regions, they are granite, very homogeneous. But thing that is this at the range we are doing the stimulation like 10,900 foot in our like in the region our stimulation. So these things like if you see the figure, it's quite a the fabric and rock fabric. These things could contribute to the complication of this initiation of these fractures. So yeah, I'm not going to read one by one. We did the preliminary precipitation matching. It is very preliminary and just here to open discussion. And we want to like refine these models, our models, by the incoming microseismicity data. Generally, so for those three stages, you can match them with the penetration crack model. And for stage 1, you can also match with the permeable DFN, permeable and friction DFN. Yeah, this is all from me.
Thanks, Pinju. So we have a few questions come in, and I'm not going to take them in order, but I'm going to send them out to the team. So I think, Karen Olson, would you like, instead of me reading your question, do you want to just come off mute and make your comment or ask your question? Or maybe Karen's having some audio difficulties. So
maybe I can address it.
Okay, well, will you read it back to the group first, John?
So Karen's observation is that, and it follows on Mark's comment too, is that if the tortuosity gradually is reduced in these wells, as you can imagine it is, you should be able to get some indication of a revised perforation friction profile by looking at the step up data, that because it was stepped up. And I think the answer to that is that no, we have not done that yet, but that's a great suggestion.
Thanks, John. Mark McClure, you have a rather lengthy comment in here, and instead of me trying to read it,
Sure.
you mind coming off? Thank you.
Yeah, sure. Yeah, thanks, Rob. Yeah, so my comment is what John just said. So when you fracture from a horizontal well, you get near wellbore tortuosity. Fracture tends to initiate longitudinally, and then it's going to have to rotate 90 degrees to become transverse. That creates a pinch point near the fracture. And so what that does is it can create an additional delta P, so that even if you account for the perforation pressure drop and the wellbore friction, you still might be estimating a number that's a lot higher than what's actually the pressure in the fracture. So, and to make it even worse, that tortuosity changes over time. As the fracture grows, it might grow back into the well and go away. So you have this additional delta P that we know is there, but we don't know what its magnitude is, and we know that it can change over time. So that's why net pressure matching is not very common in horizontal wells like in shale, for this reason, that they've got this extra issue kind of throwing a monkey wrench in it. So that's what it looks like to me, is just you've got a lot of tortuosity initially, and as the fracturing develops, that tortuosity erodes. So I wouldn't interpret that as a net pressure trend. I would just interpret that as a near wellbore tortuosity phenomenon. And so you did a step down. The step down at the end of the test, it could help understand the tortuosity at the end of the test. But if you had done a step down, after 10 minutes of injection, you might have seen something totally different. And so that was my comment.
Thanks, Mark. Colorado School of Mines, you posted you have 2 questions. The floor is yours.
John, can you hear me? This is Hossein Kazmi from the School of Mines.
Yes, hi.
Thank you very much. Number one question I have, I think, first of all, I want to compliment the effort. There's tremendous amount of data. I love it. I love the data. But my first question is, the formation itself is pretty tight. It has a lot of, has got a lot of large fractures in it, which is, mapped by DFN. But does the formation on this side, does it have, what kind of fluid has in it? Is it water, or what do you have in there?
What fluid is there will be water.
You think there is fluid in those, whatever, fractures, microfractures, you think they're filled with water? Is that correct?
Yes.
Okay. And number 2, Dr. McLaren, I'll send you an email. I don't know if you have read it or not. Can we get, a 1.5 inch by 2 inch long core plot from the matrix rock for us to do some experimental work here at School of Mines?
Yeah, I've actually passed that request on to the keeper of the core.
I'm sorry, I didn't.
I've passed that request on to see what
okay.
our inventory is.
Well, we appreciate it.
Yeah.
I think I want to again thank you all for sharing all the information, and it's incredible. But we are new to this one, and we'll be joining you in the future. I mean, we'll attend every one of these meetings, but we'll share with you what our thoughts are down the road. Okay.
Thank you. That's why we have these meetings. So
thank you very much.
All right. Sam Mondal, hopefully I pronounced your last name right. You have a comment or a question about proppants. Do you want to come off mute and ask it? I'll just read it since we don't seem to get the audio. Sam's comment was, without proppant, I would also think the change would be more in the tortuosity component than the perf component, especially with 120 shots per foot. So if you want to follow up on that, Sam, please just come back in and we'll go from there. Peter Lee, question? You want to come off mute?
Actually, based on my experience on the oil and gas frac, because these stage 2 and 3, it's a cementing casing. Stage 1 is open hole. So you will see this different. It makes the difference there. With the cementing casing, even with the perforation, you have some extra friction there. And actually in the oil and gas, we actually run the SSB ahead, and actually it dissolved the cement and actually reduced the pressure. We saw about 1,000 to 1,500 pound decrease when the acid actually went through that. And it could be the solution for these high net pressure at the beginning.
Yeah, Peter, that's a good observation. We actually had a tote of acid that was present in case we had trouble with the breakdown. I think that the issue here is, it was pointed out by Sam, is that this pressure reduction is, this pressure loss is probably not explicitly associated with the perforations. It may be more so associated with near well tortuosity, either as Mark suggested that there's an axial component, although we suspect from the seismicity that we've seen for stage 3 that the lateral extent along the length of the well of that fracture was probably not excessive, and that if I had to guess that the loss is that you are initially flowing through fractures that are inclined to the maximum, to the principal stresses. And I think that I speculate at least that the reduction in the tortuosity is associated with improved connection between the natural fractures that are present near the wellbore. And I'd welcome people's insights on that.
Thanks, John. Eric Sonnenthal, do you want to come off mute, please?
Oh, sure. Hi, interesting. Yeah, I was just wondering, maybe this is too short of a time period to be important, but did you consider any of the thermal effects? How did you do the temperature, water temperature, rock temperature?
Yeah, so for the simulation, we in the previous simulations, we did not consider thermal effect of the fracture propagation, but there's possible influence in stage 3 because in stage 3 we use cross-link gel. As time goes, the viscosity will change, will reduce with time. So that could affect your fracture propagation. That's I can think about how the thermal can affect.
Okay. Can I have another question in here?
Yeah, sneak it in there, Eric.
Yeah, I mean, I am curious about the what were the natural, how did the natural fractures that were measured in those particular sections, like the density, compared to that DFN? Because of course, DFN is great for the large system, but every little particular site may be a little different.
So I think I could take that one, at least for the initial part, for the DFN part. So Eric, we actually went through a screening and took the FMI logs along the length of the wellbore, and essentially did a summation of the number of fractures over given a 10-foot window or a 20-foot, essentially a walking window, that were angled or favorable to some, and that's a qualitative favorable to the stress regime. And by that, we actually plot, that's how we chose some of the locations to do the stimulations. But I don't have the exact number of fractures per like the perforated zone. But there's definitely a higher concentration of natural fractures were measured in 16A on the zones we chose.
However, I think Eric's question is a little more penetrating than that. Is that, did the simulations reflect the FMI signatures specifically for the entry points?
Yeah, thanks.
I'm not sure that Itasca's had a chance to do that yet. But maybe.
Not for this case, but yeah, we did the reflect the FMI fracture in the pressure case match with the defeat later, but not for this one. Yeah, so they could have some effect, but because this relative high volume and high pumping rate, this could merge together finally. So, but yeah, we did not do this multi-entry in this case.
And then maybe I'll take a crack at Karen's question.
Hold on, let me follow up there. One more thing, John, if you don't
Sorry.
mind. So Eric, to kind of further answer your question too for the thermal effects, we are actually launching a number of longer term simulations, more on a continuum basis, but also in the DFN itself, to look at longer term flow and transport now, in our stimulated volume. So we actually have, it would be a connected fracture network. Of course, that'll get better as we have the seismic data come back in. But those thermal effects for relation to permeability, fluid properties are being considered right now with a number of different methods.
Yeah, sounds great. Yeah, and regarding the fracture, yeah, you can get into all kinds of like tortuosity, and there's so many factors that affect the pressure. And then sometimes it's just like, well, maybe there were just more fractures in that zone or more, you know how it is. It's a natural system. So maybe the continuum, yeah, just a uniform permeability, a comparison. Well, what do you get? I don't know.
So what we've done, Eric, actually
on experiments.
Yeah, we've gone through and upscaled that DFN. What would be like some of the output from the simulations that Pengju just showed. We've upscaled those anywhere from a 10-meter uniform grid down to a 2-meter. We also have the DFN itself. So we're doing simulations on an assembly of 2D fracture planes and also on upscaled like permeability and porosity, or permeability tensor and porosity that'll be upscaled from that DFN. So we'll work through all those. That's a little bit time consuming, but that's all in anticipation to do better history match and help plan for 16B and for flow testing.
Yeah, that'll be just interesting, just from understanding, other than just matching. Yeah, very good. Thanks.
And the devil's in the details. We try to look at thermal stimulation, pore elastic effects as well as chemistry effects. So it's a non-trivial exercise, but it's in process right now. John, you want to go over and answer Karen's second question?
Karen, I don't think we know yet, but I think just a message to Pengju is that there's, in your bottom hole pressure, you're going to have to make a slight correction for the change in hydrostatic with the proppant, if you haven't already.
Okay, I did not consider proppant for the hydrostatic. Yeah.
Okay. The our friends at Colorado School of Mines, you can please come back.
Thank you, Rob. The question I have is this: in the stimulation, stage 1, stage 2, and stage 3, on the newest one, new injection well, what was the fracture half-length, roughly speaking? That's number one question. What's the fracture half-length? And number 2, in the modeling, was the fluid loss into the DFN or into the DFN plus the matrix? I just wonder how they did this. If the questions are not clear, I'll be glad to clear it.
So Pongju, what sort of half lengths were you getting? I mean, the seismicity shows a microseismic envelope that's pseudo-radial frac at least 300 feet in radius.
Yeah, I think this circle is like the diameter is 320 meters.
Diameter. Okay.
320 meters diameter. So
Which is probably way beyond, well, in stage 3, if I went to stage 3, that's substantially beyond what the microseismicity would suggest as a very upper limit for the radius.
How many?
That's pretty big.
How much?
And I'll note that once we get that, all the hypocenters from the microseismic, we will put those into the Earth model and Leapfrog, and that still will be available if people want it. But I'm certain that the data will also be available just as coordinates, so you can use them in your own, take them in your own post-processing, however you like.
So Peng-Shu, how did you model fluid loss?
We can talk about that. Okay, John, my question again, as I understand, the fracture half length is about 150 feet. Am I correct?
I'd say it's the half length would be 300 feet.
Half length is 300 feet. That's what you say. My question was also, the DFN was the medium through which you have leakage. You have what we call filter loss, or did you go through the matrix as well? How did you do that? Is your model is it kind of dual porosity, which consists of DFN and the matrix, or DFN natural fractures and the matrix? What's your model look like?
yeah, let me explain it. So in this DFN, so this model with this friction permeable DFN, so we don't have matrix permeability.
Okay, I got it. And let me ask you this though. I appreciate it. Let me ask you, let me have a dialogue with you. So what was, roughly speaking, the fracture spacing in your model?
Can you repeat the question?
The fracture spacing between two, DFN fractures. Roughly speaking, what was the distance, roughly speaking? Is it 20 meters, 10 meters, 50 meters?
Oh, okay. I think the minimum could be 10 meters, 20 meters. The maximum is 100 meters.
You're thinking of the links, Peng-Ju.
Is Alita on?
Alita is on. Alita, do you want to comment on that? Alita Finella from Golder Associates is the one that, essentially is in charge of our DFN creation and management. Alita?
Yeah, I'm trying to remember exact numbers. The fractures that we included, I think we had a minimum size of a radius of, I want to say 10 meters on it. And, we modeled the fracture size distribution as a power law distribution. So there's many more smaller fractures that we did not include in the model. So we had sort of a size cutoff of that 10 meter radius. So if you look at sort of the number of intersections along the wellbore for those 10 meter sized fractures, it probably was on the order of, 10 meters or so between fracture spacing on intersections.
Thank you, Alita. I think so. Basically 10 meters.
10 yeah, meters. but it is it's a 3D model with very different orientations, 4 different orientation sets. So it's not really a regular spacing.
I totally understand. But I just wanted to know exactly how you did it. And fundamentally, what I understand, the fluid loss was into these fractures. And these fractures typically, let's say, they had a spacing of about 10 meters. Because it's very,
yeah.
it's very critical, you know, when we measure matrix permeability and things like that, and y'all, as I understood, that the matrix permeability was not included in the filter loss. And of course, measuring these fracture permeabilities, I've read a lot of your reports, but I really don't know how you were able to measure those things. And so that's a question. Maybe y'all want to think about it and tell us about it and educate us. By the way, I'm questioning not to criticize the data, anything else. I'm just trying to learn, to see how these things were done. And so we appreciate anything you can teach us. We'll be your student.
Okay. I think we can move on. I understand your comments. We can, if we need to dive in further, we could do something offline. I think there may be a little bit of a communication barrier there for what we did. There is quite a bit of literature that we put out for how the DFNs were created and how they're parameterized. But we can follow up more of that later. You can just, if you want to email me, I can get your question answered by, you know, the more appropriate person. Mark McClure did come in with another question here about leak off, including into the surrounding matrix around the fractures. And I can answer that. I'll let you answer it, Pengju, but we can go.
No, we don't include leak off into the matrix. So
Okay.
that's- yeah.
Okay, thank you.
We are at the top of the hour. The questions are winding down. I'm happy to stay on as long as anyone would like. If we want to keep the discussion going, you know, I do realize most people, or a lot of people have to leave at the top of the hour. If there's no further questions, we'll say we'll get a countdown to 5. If I don't see anything pop in, we'll adjourn for the day. This meeting was recorded. Give us a few days and we'll post it on the Utah Forge website. Follow on questions, you can feel free to email me or the Utah Forge research or any number that, you know, reach out to anyone on the team. We'll get your questions answered. And we look forward to continue these discussions. You know, and later on, if there's things you didn't want to mention, you know, questions, comments, or even snide remarks, send them to me, and we'll happy to address them any way you can. So I thank everyone for joining today, and have a great rest of your day and a great rest of your week. Thank you so much.
Thank you.
Thanks, Rob. Thanks, Pengju.
Yeah, thank you, John. Thank you.
Thank you. Bye.
John, can you stay on for another moment?
Am I going to be scolded?
No, you're not in trouble.